Hello and welcome. My name is Alan Malfavon, and today I'll be discussing the Lewis dot structure, the VSEPR bond theory diagrams, the energy diagrams, and the contour diagrams for nitrite formula NO2- as part of an assignment for the second semester of general chemistry at Cerritos College. I hope you enjoyed this video and learn as much as I did about these structures. All right, we'll proceed.
Here I will be going over how to draw the Lewis dot structure for the nitrite ion. So by now you've probably looked over at the periodic table dozens and dozens of times to know that the oxygen element is in group 6A and the nitrogen element is in group 5A, which means that nitrogen will have 5 valence electrons and the oxygen atom will have 6 valence electrons. Now, to begin drawing, I prefer this method that allows me to see or makes more evident the possible bonding pairs that will occur between the central atom and any surrounding atoms of other elements. So here, beneath my yellow arrow, I have drawn the individual atoms of the ion. So we have an oxygen on the left-hand side, an oxygen on the right-hand side, with their valence electrons available for bonding. And I have traced with with light green lines the bonds that would form between the oxygen atom on the left-hand side with nitrogen and the double bond that will form between the nitrogen atom and the oxygen atom on the right-hand side. It's important to also note that beneath my first drawing here, I have circled in red the additional electron that will be added to the oxygen atom. Now this additional electron comes from the fact that nitrite has a -1 charge, and that represents the presence of an additional electron, which we will assign to the most electronegative atom within nitrite, which has to be an oxygen atom. Moving further right, we see that nitrogen will have a lone pair of electrons above it, and I have chosen to draw the double bonded oxygen atom to the right-hand side. We see that it has 2 lone pairs of electrons, which I've identified with yellow arrows there. And on the left-hand side, we have the oxygen atom with the additional electron, which also has a sigma bond with nitrogen. And I should also note that the oxygen atom on the right-hand side also forms a sigma bond in addition to a pi bond with the nitrogen atom. Another method that is commonly used is to determine the total electrons available or found in the nitrite ion. So if we move over here to this yellow arrow, we are now at the total electrons in nitrite, and we know that the total electrons is the sum of the valence electrons present or offered up from each individual atom. So nitrogen will contribute 5 electrons, and since we have 2 oxygen atoms which have 6 valence electrons each, we will have the sum of 5 plus 12 plus 1 additional electron, bringing our total to 18 electrons available in the nitrite ion. And beneath the total charges, I have written the formal charges that occur in the ion. So nitrogen will have a formal charge of 0. Now the informal way to remember this is to subtract the sum of the non-bonding and bonding electrons from the valence electrons for each atom. So in the case of nitrogen, nitrogen has 5 valence electrons, and we deduct the sum of the non-bonding and bonding electrons, which would be the 2 non-bonding above it and then the three bonding regions, or excuse me, the three bonding pairs. We have one to the left of nitrogen and two to the right of nitrogen. Another informal way is to remember it as valence minus dots minus dashes. So for the oxygen atom on the left-hand side, and I've noted it here with this yellow arrow, we have a formal charge of -1 because we know that if there should be a formal charge, a negative formal charge, it should be assigned to the most electronegative atom, and oxygen is further to the right in the periodic table, so it is more electronegative than nitrogen. So the oxygen atom on the left-hand side has a negative charge, or excuse me, a formal charge of -1 because we deduct 7 from 6, and that gives us a net of -1. However, the oxygen atom on the right has no formal charge, or a formal charge of 0, because we deduct 6 from 6 and we obtain 0. So here on my right-hand side, I will move back to the top right column. I have drawn what's going on before our final Lewis dot structure is presented. So now that we are here, we see that the lone pair will cause the shape of nitrite to be bent as opposed to linear. If we first do a preliminary drawing of nitrite, we might assume that it should be linear because of the bonds form, and it kind of does look that way. But we know that the lone pair bonding pair repulsion would be greater than the bonding pair repulsion between the oxygen atoms. So if the oxygen atoms are already at a default of 120 degrees apart, then the presence of a lone pair of electrons above the nitrogen would further compress that angle. So it would squeeze the oxygen atoms closer together. So what was once 120 degrees will now be less than 120 degrees. Because, again, lone pair bonding pair repulsion is greater than bonding pair and bonding pair repulsion. And I have also identified, again with a negative sign, the formal charge on the leftmost oxygen atom in nitrite. Lastly, here I have drawn the Lewis dot structure for the ion using brackets and the 1- to denote the formal charge of -1, which agrees with my listing of the formal charges here. So if we did this correctly, we should obtain the same formal charge as we see on the right. I will highlight in green. So these here in blue, I will write it out. So we have 0 plus -1 plus 0 is equal to -1. And this agrees with the formal charge for the anion that is found outside the brackets in my Lewis dot structure. Here I'll be going over how to draw the Lewis dot structure for the nitrite ion. Here I have drawn 3 diagrams for nitrite which demonstrate its electron geometry, its molecular geometry, and also the hybridization orbitals that correspond to the number of electron orbitals around the central atom, which for our ion will be nitrogen. And at the very end on the right, I have re-included my model kit representation of nitrite. We'll see that the blue orb in the middle is the nitrogen atom, and it has 2 double bonds with the oxygen represented by the red orb on the right-hand side, and it also has another bond with the oxygen atom, again the red orb on the left-hand side. So we can say that because nitrogen has 3 electron regions, which I've highlighted in green,
that its electron pair geometry is trigonal planar. They're all in the same plane. Moreover, because of the lone pair above the nitrogen atom, as reflected in my second diagram, that lone pair has a repulsive effect that is greater than the single bond repulsion and the double bond single bond repulsion. So this lone pair of electrons is pushing down on the angle that we understand to be 120 degrees and making that angle between the oxygen atoms even smaller. So instead of having a trigonal planar, which is the default, instead of having a trigonal planar molecular shape, we would say that its molecular shape is bent. I have drawn arrows in blue, signifying or identifying the repelling electron fields. So there's one above the nitrogen atom, again representing for the lone pair, and then there's one for the nitrogen-oxygen bond on the left-hand side, and another for the double bond region on the right-hand side between nitrogen and oxygen. So if we had to identify the angles, which I'll draw with a yellow arrow here, are less than 120 degrees, while these angles above are both greater than 120 degrees, because if you can imagine yourself being at 120 degrees and you're pushing downward on another equiangular angle, then your own angle will be increased, while the other diminishes. So lastly, we can see that we know that 3 electron orbitals corresponds to hybridization orbitals of sp2, because there are 3 electron regions, 1 s and 2 p's. And lastly, we can see that our Lewis dot structure closely resembles, it's not too far away from the imagination of what we can represent the nitrite ion as in a model kit. Next, I will be discussing the energy diagrams available for nitrogen and the oxygen atoms attached to nitrogen in nitrite. So for nitrogen, we start off with our ground state, which we know is 1s2, 2s2, 2p6. And we know that we'll need an sp2 orbital after hybridization. So in the center, I have circled in a light green the electrons that are going to take part in this hybridization. We can see that we will have a lone pair plus 2 electrons that are available for the sigma bonds to form with each oxygen atom, and an additional electron in the 2p orbital that will form in a pi bond with the oxygen, which I have drawn on the right-hand side. So if you follow the diagram I have included on the right-hand side for each atom, you can trace lines I have provided for where each electron in green will be coming from to fill the sp2 orbitals and the 2p orbital in the sigma bonds and pi bonds the pi bond respectively. So we can see that after hybridization, we have a lone pair in the sp2 orbital, and we have 2 upstroke electrons. And I have traced lines from the pi bonds between nitrogen and both oxygen atoms to show where the other electrons are coming from. So we will have an electron coming from the right-hand side, oxygen, in that pi bond, and also an electron from the sigma bond. Oh, excuse me. I meant to say that we will have two oxygen sigma bonds contributing an electron each for the sigma bonds between nitrogen and oxygen in the sp2 orbitals. And in addition, the pi bond between nitrogen and oxygen on the right-hand side will have a shared electron in green in the 2p orbital, traced by the orange line from the right. Similarly, or I should say alternatively, the pi-bonded oxygen atom, which has a ground state of 1s2, 2s2, 2p4, will undergo hybridization to form sp2 orbitals. So, again, I have circled in light green the electrons taking place in the hybridization. So after hybridization, we see that we will have two lone pairs, plus an additional electron available for the pi bond in a 2p orbital that will be shared with the nitrogen atom. So again, using the diagram on the right, we see that we have the two lone pairs on the oxygen atom. We have a free electron found in the sigma bond with the nitrogen, and an additional electron forming a pi bond with the nitrogen atom. The green lines represent what would be the shared electrons, and the red lines I have traced from the sigma bonds, and orange for the pi bond. Lastly, we come to the sigma bonded, or the exclusively sigma bonded oxygen atom for nitrite. Again, we begin with the ground state of oxygen, 1s2, 2s2, 2p4, and then we identify that after hybridization we will have sp3 orbitals. So not sp2 but sp3 orbitals, because this oxygen atom has 4 electron regions. It has 3 lone pairs and 1 bonding pair, as opposed to previously we had an oxygen atom with 3 regions. We had two lone pairs of electrons and a region including a double bonding or double bonds. So coming back to this oxygen atom, we have sp3 orbitals, and we see that we have the 3 lone pairs which are required. That checks out. But we also have a single electron available for bonding, and for bonding with the sp2 orbital in nitrogen, or of nitrogen. So we will have 3 lone pairs plus a shared pair of electrons between the oxygen's sp3 orbital and the nitrogen's sp2 orbital. This is further exemplified in the contour diagram below. I think it'll be clearer to you that what the shape of this nitrite ion will look like.
Below I've included my drawing of the contour diagram for nitrite. We can see that I have arranged the atoms in a fashion that appears to be bent as it is found in my Lewis dot structure. We have nitrogen in the center and 2 oxygen atoms to the left and to the right, about 45 degrees away from, or excuse me, with a about 45 degree inclination from nitrogen. So we see that nitrogen has 3 sp2 orbitals. It has 1 lone pair above it and 2 electron pairs that are shared with either of the oxygen atoms. The oxygen atom on the right has, or I should say, in addition to the sigma bond formed between the sp2 orbital of nitrogen and the sp2 orbital of oxygen, has a pi bond, which I have drawn in orange. So this pi bond is found above the sigma bond, and it is denoted by an sp2 orbital with you see the blue electron dot which shows the proposed path or proposed location of the electron in those orbitals. I have also connected them with blue dashed lines so that you may see how you may see their proposed movement. The oxygen atom also has the two lone pairs, which are further to the bottom right of the oxygen atom, also found on the right-hand side. They are found in sp2 orbitals. Moving to the left-hand side, we see that nitrogen has a sigma bond formed with the oxygen atom. Now, this oxygen atom is the oxygen which has the additional electron, because nitrite has a formal charge of -1, and that -1 was assigned to the left-hand side electron previously. So this electron atom has three lone pairs, which are found in the sp3 orbitals, which I have drawn in green. So we have 1, 2, 3 lone pairs of electrons, and we also have a shared pair of electrons in the sigma bond between the sp3 orbital of oxygen and the sp2 orbital of nitrogen. Following the solid blue line between the oxygen atoms, I have identified how the lone pair of electrons in the sp2 orbital above nitrogen would have a greater repulsive effect than the bonding pair repulsion between the oxygen atoms. So again, lone pair bonding pair repulsion is greater than bonding pair repulsion. So what was once 120 degrees is now being pushed, or that angle is being diminished. So the oxygen atoms are being pushed closer together by the repulsion effect of the electron pair above nitrogen. Because this is a trigonal, we would say that nitrite has electron geometry that is trigonal planar. However, using VSEPR theory to draw the VSEPR diagram, as we did earlier, we covered how the lone pair would push the push the electron regions between the oxygen atoms closer together. So that angle, which was once 120, will now be diminished to less than 120, making this a bent shape. So we would say that nitrite has electron geometry that is trigonal planar, while its molecular shape appears to us to be bent.